Welcome to Learning Python. In this session, we'll be discussing how to measure the statistical dependence between two variables. Remember, here we are talking about statistical dependence. It does not mean physically they are related or not related. There are many other ways like causality and many other things we can do to figure out whether there is a physical connection between two variables or not. In this session, we'll restrict ourselves to statistical dependence. To understand how we can do what are the limitations, we'll generate six relationships. Three are perfect, three has some noise into it. So we are generating one perfect linear relationship, with no error term, nothing. Then we are generating linear with some noise we are adding. We are taking one monotonic. So monotonic means mathematically we can say if the slope is either positive or negative and but the same slope, okay, then it's monotonic. Or we say monotonically increasing when slope is positive always, or monotonically decreasing when the slope is negative always, but it's monotonic. Then second one, monotonic with some noise. Third one when it's not monotonic, and fifth one and sixth one, it's not monotonic but also there is a noise. So we are, let's open this in Colab. And whatever we discussed, we are generating those relationship, those numbers we are generating, and we'll plot it. So there is nothing so much complicated or magic about it. So we'll just look at the graph, let it come. So you can see A is the one where we have perfect linear. B is the one where we have let it come, linear with some noise we have added, so you can see it's not perfect linear. Then C is the one where we are talking about the monotonically increasing function. D where we have C plus some noise is added. Then we have E which is not monotonic. You can see one side slope is negative, one side slope is positive. Then F where E plus some noise is added. Now we look at some of the commonly used measure of statistical dependence and see what kind of result we are getting. So first we are printing between the x and y1 which was perfect, and we are getting the Pearson correlation is equal to 1. So it means it's able to capture the strength of the relationship. Then we are looking at the second one where it was perfect plus some noise, so we expect it to be slightly less than 1. So we are getting 0.94 which is perfectly fine. So it means it's able to capture the strength of the relationship. You can try increasing the the magnitude of noise, decreasing the magnitude of noise, and this 0.94 should correspondingly increase or decrease. So you can see how it's working. So far so good. So Pearson correlation is doing good job. Let's go to third case. We know third case is the quadratic function, or this function, the C part, where it's perfect relationship, okay, there is no noise in it. So we should expect for any good dependence, statistical dependence, it should give value the highest value, which is 1 in this case, but it's giving the value of 0.97 also. Even when we slightly add noise into it, it's giving 0.97. So we can see Pearson correlation is giving reasonable measure of the statistical dependence, but not the perfect, because if it was very good it should have given 1 when there was no noise, which is not happening. And also it's not able to distinguish between when we have some noise and when there is no noise. So it's not the perfect variable to capture the strength of the relationship when it's not non-linear, even though it's monotonic. Then you look at the last two cases, one where we have the it's not monotonic, we are getting 0, but the relationship was perfect, at least on the one side. We'll go into that part, what is one side, what is one two side. When we add slightly noise, then also again it's close to 0, it's point slightly negative. So we can see Pearson correlation is doing very good job when it's perfectly linear. But it's linear relationship we are talking about. It's doing reasonable job when it's not linear but close to linear. You look at the strength, it's not very far from, for a reasonable part of this a line can be fitted. But as you move away from linear and it's not monotonic, it's doing very very poor job. So with some simple experiments we are able to understand what is the strength and weakness of the Pearson. Now let's look at Spearman correlation and we run it. So what is happening here? We are getting this nearly same behavior for the linear. For the, but you see here what is happening for the monotonically increasing. It's giving the value of 1. So it means Spearman correlation is able to capture the behavior perfectly in the case of monotonic function also. It doesn't have to be linear or nearly linear. So it's doing good job. So whenever you are in a situation, you can compare Spearman also, you can compare the Pearson also, and then you can figure out whether maybe there is a chance it's not perfectly linear, but there is some other kind of relationship which exists. So you can try it. But again, it's doing poor job when we have a the function is not monotonic. So even Spearman is not helping for that part. We can compute Kendall's tau. Again, you can see the same behavior, like nearly same as the Spearman. In the case of monotonic, it can capture the strength, but not in when in the case of circular or this thing, when it's not monotonic. You have negative slope also, you have positive slope also. And why this is happening? We were talking about one way and two way. Let's go back to our example. See what's happening here. Look at the A. Let's say if we take any value of on x-axis, let's say 5, you get one value on the y-axis, so it's perfect. You go to B, you take one value, let's say 5, you get approximately same value. So we know it's not 1, strength is not 100% or 1 maximum value, it's slightly less than 1. You go to C, we can see for a value of x is equal to, let's say 5, we get one value of y, so we can figure out. And this the Spearman is able to capture it. When we go to D, it's slightly same value for the one value of x, so we can capture it. In the E, what is happening? For the same value of x, you have same value of y, one value of y, but for a single value of y, you get two value of x, and nearly same thing in the F. So it means any the statistical dependence which has the symmetric behavior, means let's say if you say correlation or say whatever you want to say, x of comma y is equal to y comma x, so you capture x versus y or you capture y versus x, you get the same behavior. It cannot capture such kind of the strength, because here the case is not this. For a single value of x, we get the unique value of y, but for a single value of y, we get two value of x. So it's not symmetric, and we cannot these kind of statistical dependence cannot capture this kind of variable. So we'll look into it, what can be done for that. But it's important to remember what is the strength of Spearman, Pearson, and this Kendall's taus, where they can be used, where they cannot be used, what they can do, what they cannot do. Because correlation is very very commonly used. We are not going into causation here. Maybe I'll try to take some real life data, and we'll see what is causation, what is not causation, and whether the statistical dependence also means physically variables are correlated or not. So that's it. It's very very important thing. I say this thing for many things, because I think I have tried to put whatever I feel is useful to solve the real type problem in this book. Yeah. Thank you. See you in the next session.